Hi all. For section 2.8, the only topic in the entire section that we're looking at is the intermediate value theorem. Now, this is a theorem that really should be fairly common sense, but a lot of students really struggle with this theorem. So what the intermediate value theorem is based upon is that it only applies to continuous functions. Remember, continuous functions have no gaps, no holes, no asymptotes over the region of their continuity. So if we say if f is continuous on some closed interval a, b, and n is some number between the y values f of a and f of b, then there exists some number c belonging to the set that script lowercase e means belonging to. Then there exists some number c belonging to the set of values between the x values of a and b such that f of c is equal to n. So a picture's worth 1,000 words in this scenario. So let's say I have some continuous function between the x values of a and b. And I tell you that f of a has this y value up here, f of b has this y value down here. I ask you to tell me, does this function take on a y value of n, which is in between f of a and f of b on this interval? You say, well, it would have to, because the only way that it would not take on a y value of n that's in between f of a and f of b is if there would be a hole in the graph at that point. And the whole definition of continuity means it can't have a hole or an asymptote or a gap. It has to be a nice continuous function. So you know that for any y value in between f of b and f of a, there exists an x value that we're calling c, where f of c is equal to that y value of n for any y value in between these two. Now you might think, well, okay, that seems pretty obvious, but how does that help? Where that's going to help in most scenarios is trying to show that a function is equal to 0. Quite often, we can have functions and it's very difficult to find their x-intercepts. What if the function doesn't factor well? What if it's a combination of a polynomial and a trigonometric to where you would have to use a graphing calculator to tell you the value? Well, instead of doing that, what we can do is we can just say, well, we know that both are continuous. I can find one x value that gives me a negative y value, one x value that gives me a positive y value. Then I know that there's some x value in between the two x values that I found that has a y value of 0 that proves the existence of a solution. Now, let's think about how that's going to apply in our first problem here. Now, when we're doing these, you'll see I finished the problems with a QED, quod erat demonstratum, because this is technically a little mini proof. It's a very simplistic proof, but it's a proof nonetheless. We are proving a certain characteristic of a function without actually finding it. In this case, it says, use the intermediate value theorem, and often we'll abbreviate the intermediate value theorem with IVT. Use the intermediate value theorem to show that the equation cosine of x is equal to x has a solution in the interval 0 to 1. Okay, so first thing I'll do is try to make this equation easier to work with. I would rather go ahead and let f of x equal the left-hand side minus the right-hand side and call f of x the function cosine of x minus x. Why would I prefer to do that? Because it's a lot easier to show that f of x must equal 0 than to show the left-hand side must equal the right-hand side, in my opinion. And I know that if I can show that f of x is 0, well, then that means that the original function had to have the left-hand side equal to the right-hand side, because that's the only time where the left minus the right would equal 0. Okay, so now I have my function defined, cosine of x minus x. I know that the cosine of 0 is 1, so you'll see I went ahead and plugged that in because I knew it would be a very small positive y value. The cosine of 0 minus 0 is the cosine of 0, which is 1. So now I'm thinking, well, all right, if I just go to a positive value of 1 now, if I test the other hand of this interval, f of 1, it's the cosine of 1 minus 1. Well, if you go to your calculator, you'll see that the cosine of 1, and please remember your calculator needs to be in radian mode anytime you're doing these. The cosine of 1 is approximately 0.54. So I said, well, the cosine of 1 is 0.54. When I plug 1 in for x, we're saying the cosine of 1 minus 1. That gives me 0.54 minus 1, which is approximately negative 0.46. Again, I'm using a calculator approximation there. So I did the approximately equal to signs, just showing my answer is an approximate answer. It doesn't matter that it's approximate answer because all I needed to know is that one x value gave me a positive y value. The next x value gave me a negative y value. So we are 100% confident that there exists some x value in between these two that has a y value of 0. You can't go from a y value of 1 to a negative y value without passing a y value of 0 for some x value in between here. So how do we make that statement as in accordance to the intermediate value theorem? We do this. Since f of 0 is 1 and f of 1 is a negative 0.46, we know, remember this is there exists, we know there exists an x, and the intermediate value theorem calls the x value c. So we know that there exists an x value equal to c belonging to the set of values between x equals 0 and x equals 1, where what? Where f of that value of c is 0. Now, you got to understand that proves the original because I have shown that there must exist an x between 0 and 1 where the y value is 0. And if I've shown that there exists an x where a y value is 0, then that means that the original equation has to be equal to one another because that's the only time the function could equal 0. So I can just say, yeah, this is conclusive evidence according to the intermediate value theorem that there has to be a solution between 0 and 1. Now, the only way we could find that solution would be using a graphing calculator or some other mathematical software. That's not something you can just handle by hand there. Similarly, look at this next problem I have here with a cubic equation that is certainly not factorable. X cubed plus 2x plus 1 is set equal to 0. So I can say, well, the left-hand side is prime. Does that mean it doesn't have a solution? Nope, it doesn't mean that. It just means that if it does, or any solutions it has will probably be irrational solutions. Now, I'm asking you to find the solution within 1/2 of a unit. So the first thing I did here, and this one really didn't help, but it's not wrong. I said, how about we evaluate our function at 1? I did that. F of 1 gave me 1 cubed plus 2 times 1 plus 1, gave me a 4. Since that was a y value pretty far away, I'm pretty sure that that wasn't going to be beneficial. I probably need a y value closer to 0. So I said, well, all right, how about I plug in a 0? Well, f of 0 is just going to give you 0 plus 0 plus 1. We get a y value of 1. Okay. So I know when I lowered the x value here, the y value lowered here. So I tried lowering it again. And this time I knew I wanted the solution within half a unit. So I went to x equals negative 1/2. And I said, what about if I plug in a negative 1/2? I get negative 1/2 cubed plus 2 times negative 1/2 plus 1. Well, negative 1/2 cubed is a negative 1 over 8. And then this is just going to be minus 1 plus 1. So those counteract each other. And I just have a negative 1 over 8, which is fantastic because now I know, hey, I found an x value that gives me a positive y value. I found an x value that gives me a negative y value. So I know there is a y value of 0 somewhere in between those two x values. Gorgeous. I state that by the following. Since f of 0 is 1 and f of negative 1/2 is a negative 1/8, 1 over 8, we know there exists an x equals c belonging to the set of x values between negative 1 and 0. You always want to go low to high in these interval notations. So there's an x value equals c belonging to the set of values between negative 1/2 and 0, square f of c is equal to 0. And again, guys, that's guaranteed by the intermediate value theorem, because we know that this x value gave you a negative y value. This x value gave you a positive y value. So there's some x value in between there that's going to give you a y value of 0, and that's precisely what we were trying to show here. And this is thanks to the continuity of all trigonometric functions. This has to be true. All right, guys, gorgeous section. Unfortunately, when you look on Achieve, it's not fun problems on there. You can probably answer them without showing out all of the gorgeous work, because they just want a numerical answer most of the time on all of those. I hope you do look at either the scan of my Achieve work for that section, or else the Achieve videos for that section. That will show you what you're really supposed to be doing in each of those proof problems. If I have an intermediate value theorem on the test, I will want you to use the logic of the proof in order to show these out. All right, guys, that'll do it for 2.8. Next up, we have the definition of a derivative with Chapter 3. Absolutely cool stuff.